Hello, so we're on the third lecture for Chapter 3, 3.3, the mole. The molecular mass, or the molecular weight, is the sum of all the atomic masses in atomic mass units of all the atoms that are in a molecule or a formula unit if it's an ionic compound. So for example, we're going to calculate the molecular mass of a molecular compound as well as an ionic compound. So dinitrogen pentoxide is our molecular compound. So dinitrogen pentoxide is N2O5, and here are elements from the periodic chart. We need to look at their atomic masses. So 14.01 for nitrogen and 16.00 for oxygen. And we multiply that by how many atoms are in the molecule. So 2 for nitrogen and 5 for oxygen. So we multiply those and we get 60.02 units. Now, these are atomic mass units, and we know that protons and neutrons are weigh one atomic mass unit each. So these are really, really tiny amounts. In our ionic compound, we have sodium permanganate. Sodium, manganese, and oxygen. We have one atom of sodium, so the 22.99 atomic mass units. We have one atom of manganese at 54.94 atomic mass units, and we have four atoms of oxygen at 16.00 atomic mass units. I messed up here. That's supposed to be a 664, and when we 6 and 5 is, I believe that should be 146.93 atomic mass units. I apologize for that. So 64 right here, and have to re-add that. Avogadro's number is the next topic in this section. It has a symbol of capital N, and it is equal to 6.022 times 10 to the 23rd power. So this number has 24 digits, and it is really, really big. In 1909, there was a French atomic physicist by the name of Jean-Baptiste Perrin, and he coined the term Avogadro's number for the number of molecules in 1 mole of molecules. So he was doing work that was involving the same things that Avogadro had studied before, almost 100 years before. So it's a great misconception that Avogadro is the one who came up with this number. Jean-Baptiste Perrin coined that name in honor of Avogadro, and he later won a Nobel Prize for this discovery in 1926. So just remember, for right now, we'll explain what it is in just a minute, but 1 mole is equal to this really huge number, 6.022 times 10 to the 23rd power, and that is equal to 1 mole. So what is a mole? That's a really weird name, but if you think about it, there's a lot of words that we grew up learning and knowing what number it refers to. For example, you've got on a pair of shoes, you know that's 2. You have a dozen eggs in your refrigerator, and you've all heard the Abraham Lincoln's Gettysburg Address 7 years ago. So just like pair, dozen, and score, the word mole refers to a specific number, as weird as it is, but it's 6.022 times 10 to the 23rd power. So, written out It looks like this with all 24 digits there. It is the number of atoms, molecules, or ions in 1 mole of a substance. Atoms, molecules, and ions are really small and impossible for chemists to count. But using this amount, if you have this many of them, it's easier to talk about the amounts and weigh them on a scale, um, and discuss what kind of reactions happened, and keep track of the quantities of each substance that's being studied. So if you look down here, and we see lots of familiar things. There is water, iron, oxygen, table salt, gold, and helium. And in the icons right here, it has different numbers of grams. So water, 18 grams, iron, 55.9 grams, and so on. Now, if you look at these numbers and compare them to the periodic chart, to the atomic masses listed on the periodic chart, I hope you see some similarities jump out at you. So look at helium first. So element number 2 has an atomic mass of 4.003 atomic mass units. And here on this balloon, it's got 4.00 grams. Now, if you look at element number 79, gold, it has an atomic mass of 197.0 atomic mass units. Here, it's got 197 grams. Now, if you add the masses of sodium and chlorine together, you're going to get 58.4 atomic mass units. And oxygen, 2 oxygen atoms would weigh 16 atomic mass units. Iron, you're going to see 55.9, and water, if you add the masses of 2 hydrogens and 1 oxygen atom, so you'd get 18 atomic mass units. So this converts, this number is weird, but it is the magic ratio that converts atomic mass units to grams. So if you had 1 atom of carbon-12, its mass would be 12 atomic mass units. But if you have 1 mole of carbon-12 atoms, so if you had 6.022 times 10 to the 23rd carbon-12 atoms, then you would have 12.00 grams of carbon atoms. So this is wonderful. Avogadro's number was a huge breakthrough in chemistry because this ratio works for all of the elements, not just carbon. 1 mole of any element weighs the same as its atomic mass amount, only in grams. Very, very handy. So from now on, now we know about atomic mass using the units, and now molar mass. So the molar mass of something is the mass of 1 mole of that whatever substance it is. So first of all, we're going to calculate the molar mass of sucrose. Now, sucrose is table sugar, the granulated white sugar that you put in your coffee or on your cereal. C12H22O11. So we're multiplying 12, since there's 12 carbons, 12 moles of 12 times 12.01 grams per mole for the carbon, and we get 144.12 grams. We're multiplying 22 moles times the molar mass of hydrogen and 11 moles times the molar mass of oxygen. So we cancel out the moles, and that leaves the grams. We add them up, and we get 342.296 grams. Now we need to, before we circle our answer and move on to the next problem, we need to think about significant figures. So when we're adding, we go by whatever the last common digit that they all have. So this one right here has a thousandths place. The rest of them stop at hundredths place. So if we were only adding, we would cut that, well, we'd round up one and make this 0.30 if we were just adding. But we had to multiply as well. Now, the 12, the 22, and the 11 are exact numbers because every molecule of table sugar has exactly those numbers of atoms. So we don't have to limit our answer to 2 digits, but instead we look at these numbers. So all of these numbers have 4 significant figures, okay? And 4 significant figures is when we compare that to if some of these would have 5 significant feet, well, they'd wind up having 5 if we just got rid of the thousandths place. So we need to have our answer with only 4 significant figures because this one has the least. So that means that we look at the 5th digit and see if it's 5 or greater. So 1, 2, 3, 4. This one's the 5th digit. 9 is bigger than 5, so we need to round this to 342.3 grams. So we have 4 significant figures in our answer. Now, so if we had 342.3 grams of table sugar, we would have 1.7 cups of sugar. So that's a pretty large amount. Sometimes a mole of something is a large amount and sometimes it's not. It just depends on how big of a molecule it is, or there's a lot of variability. But it's way easier to weigh and to measure than atomic mass units. So now be really careful and pay attention if it's asking for the molar mass or the atomic mass. So this one is calculate the molecular mass. The molecular mass would be the same as the atomic mass. We're talking about molecules or the atoms. It doesn't mention moles. Okay. Calculate the molecular mass of methane, CH4. So we need to multiply. There's 1 carbon and there's 4 hydrogens, and we find their atomic masses 12.01 and 1.008. We multiply and add these 2 things together, and we should get 16.042 atomic mass units. And if we let's see, we've got 4 significant figures here, and we have 4 significant figures there. Our answer should have 4 significant figures in the answer. So 1, 2, 3, 4. We look at the 2 and it's less than 5, so we do not round up. We just chop it off, and our answer is 16.04 atomic mass units. So this is a very tiny amount. This is just the mass of 1 molecule. So molar mass will be in grams, while molecular mass or atomic mass will be in atomic mass units. All right. Let's skip on to page 73 in your book where it says the review exercises. So let's look at number 10. How many water molecules may be found in 2.5 moles of water? So what is that asking? 2.5 moles of water. So that's kind of similar to how many eggs may be found in 2.5 dozen eggs. So do you see the difference? It's wanting a number. So how many moles, how many dozens, or how many pairs? So a mole is 6.022 times 10 to the 23rd. So we've got 2.5 moles of water. We need to multiply by 6.022 times 10 to the 23rd water molecules. That's how many molecules are in 1 mole of water. And we need the moles of water to cancel out. So I didn't have the little lines to cancel them out. But if you multiply 2.5 times the mole, you're going to get 12.044 times 10 to the 23rd. Now, that's not proper scientific notation. We have to have just one digit. We have to have just the ones placed. We need to move that decimal over. So to make it in scientific notation, when we move that decimal over, that makes one more over here. So 1.2044 times 10 to the 24th water molecules. And I messed up. We should have two significant figures here. This number is the standard number that's accepted. So this is the limiting number. It should be 1.2 times 10 to the 24th and chop off the last three digits. So our answer is 1.2 times 10 to the 24th power water molecules. What would be the mass in grams of 2.5 moles of water? So this is question 11, and we're going to figure out. So we counted how many molecules it is in 2.5 moles of water. We're going to find out whether it's a giant wave of water or if it's a little tiny glass of water. So you can think ahead which one you think it's going to be, make your guess, and let's calculate and see. So also notice they were really nice this time and specifically asked for the mass in grams. So what would be the mass in grams? So you don't have to wonder or guess. So we're going to multiply our 2.5 moles of water times 18.016 grams of water in 1 mole of water. So that's just adding the mass of 2 hydrogens and 1 oxygen, the molar mass of each of those atoms in together. So 16.00 plus 1.008 plus 1.008. That gives us 18.016. So multiply those, and the moles of water cancels out. So 2.5 times 18.016 is 45.04 grams of water. Now, again, I messed up and I didn't do the significant figures. 2.5 would be 2 digits, and this has 5 digits. So this is the smallest one. That's what we have to go with. And our answer should have just been 45 grams of water. Oh, I did do it. I forgot. So 45 grams of water is the significant figures of this calculation. If you remember, we've talked about it a few times in lab class. 1 cubic centimeter or 1 milliliter of water weighs 1 gram. So that is just amazing about water. So that 45 grams of water means there's 45 milliliters of water. So 45 milliliters of water is a little less than, I believe, a quarter cup. So it would be more like this picture than like this one. This would be way, way more. So check mark if you guessed the little glass of water. So just to recap, these are all the things that we've learned in Chapter 3, how to name molecular or the covalent compounds. They were nonmetals to nonmetals. how to name ionic compounds. These were metals bound to nonmetals. How to calculate molecular mass, what and how many is a mole, and how to calculate molar mass. And just to be funny, here's this uh, little thing about Avogadro. Abby looked at, I was lamenting about how terrible his face looks. And Abby looked it up, and it turns out that they got his image from his death mask. So I don't know how old he was when he died, but apparently there was a death mask made, and then they tried to figure out using that mask and imagine what he would have looked like when he was younger. So they did not have his picture, and this is probably nothing like what he really looked like. So um, it it looks pretty scary looking. Um, but this is in the elevator, like when the girls were taking violin lessons, there'd be these little signs and have phone numbers for people to call about if they were wanting to buy their textbooks or whatever. So um, this just, so here's his number. That's all I have. We don't have a test till chapter 4. So talk to you all again soon. Bye.